Now that we've seen how we can add vectors together in 2 dimensions by breaking them down into their Cartesian component form, let's extend that now to working in 3 dimensions. So the idea is still going to be basically the same. We need to represent all of our vectors in Cartesian component form before we do any operations. The difference now being that there's going to be an I, a j, and a k component in this Cartesian component form, the k representing how much of our vector is in the z direction. We're going to then add the like components together, and the same thing is going to happen. We're going to get this resultant vector, and it still represents the net effect of now these multiple 3D vectors acting simultaneously. Now, it's not going to be easy to do if we're not in Cartesian form. Just like we saw in 2 dimensions, the polar form, we can't just add the magnitudes together, add the directions together. We have to go into this intermediary step of the Cartesian form. Same thing is true in 3D. If we're given some spherical coordinates or some cylindrical coordinates, we can't just add the magnitudes and the directions. We need to go into the Cartesian form first. What we're going to see in subsequent slides is that any vector f represented here is equal to some magnitude times a direction. And we can represent that magnitude by scalar f times this u hat, which I'll address in a couple of slides here. So it's going to be the magnitude of the vector times its direction times its unit vector. That's what u hat is representing. And this is the direction of the vector is the collection of its direction cosines, it's often referred to. And this u hat is a unit vector being a vector that has a magnitude of 1. So how do we go into this component form when we're in 3 dimensions? Well, there's going to be different ways that a vector could be given to us when we're in 3D. Maybe we're presented with a vector's magnitude, and case A, we have the angle that it makes with all 3 positive axes. I'd say this is not usually the case in this class, but sometimes in like robotic systems, we would know the magnitude and the angle it makes with all 3 axes. So it's important to at least understand how we can go from this representation to our Cartesian component form. This is actually the easiest case because if we know the angle that the vector makes with all 3 axes, what we can simply do is take the cosine of each of those angles, and that is going to be the components of this u hat vector. These are the direction cosines. And we'll see that on a subsequent example. Now, possibly we're given the magnitude of the vector and then the angle it makes with a plane in our coordinate system, and then angle it makes with an axis within that plane. So kind of similar to case A, but we have an angle to a plane and then angle to an axis, rather than the angle to all 3 of our positive axes here. And what we'll be able to do in the example is we can break this down into 2 right triangles. Again, typically we don't see case B either for this class in how a 3D vector is going to be represented. Most of the time we are going to see case C, where we're going to know the magnitude of some vector, and then we're going to be given 2 points through which it passes. So what we're going to be doing in this case most commonly is we can write down all the coordinates that are going to be important in our diagram, and then what we're going to be doing is finding what's called the unit vector, or the direction of this vector. So it's the direction that passes through those 2 points but has a magnitude of 1. So finding this unit vector is going to be the first step. So how do we go about finding that unit vector? Well, previously I said that any vector f could be represented by its magnitude, scalar f, times its direction, u hat. So this u hat again has a magnitude of 1, it's a unit vector, and it's just telling us about the direction of the vector. Right, so what this tells us is often if we're given information about 2 points that a vector is passing through, the unit vector is going to have a magnitude of 1 but point in the same direction between the start point and the end point. So the magnitude is going to be different, but it still points along that same axis that passes through those 2 points. So this is useful in times where we know 2 points a vector passes through. So for example, if we have like a cable or a rope that's tied to a point A and a point B, well, if we want to know the force in the rope, we know that that force, though the magnitude is certainly different than the rope it lies on, because the force will be in like newtons and the rope's length is going to be in meters, we know that what they will share is the same direction. The force in the rope passes through the axis that the rope lies on. So we are trying to find that axis. So we have more information about that force vector. So what we can do is we can start typically with a position vector that points from, again, in this example, let's generically say it points from A to B. So what we want to write down is vector R sub AB is typically how we represent it. And from there, if we know the position vector that points from A to B, we're going to be able to calculate the unit vector that passes from A to B as well. So we can denote that typically by U hat AB. So the first letter is where the vector is starting, and the second letter is the direction at which it points, or the second point that it passes through. So like U hat AB is going to be different than U hat BA. They're actually going to be negatives of each other, but their directions are opposite. So how do we first find this position vector? Keep calling it RAB for now. Well, RAB is going to be found by taking its end point minus the start point. So where does it end minus where it starts? And this is where using a coordinate system in our Cartesian coordinates is going to be really helpful, because if we know the coordinates of point B and the coordinates of point A, well, if we take the coordinates at B and subtract the coordinates at A, we're going to very quickly be able to find the I, J, K components of this RAB. So right away, RAB, we're going to typically be able to write in this Cartesian component form. And we know from previously that that's kind of the starting point to be able to do any operations with a vector. Start in its Cartesian component form. So that's what we start with, is finding that position vector in component form. Now, how do we find the unit vector? Well, once we have the position vector, it's relatively easy. The unit vector is just the normalized, we call it, position vector. A normalized vector is just a vector that we divide by its own magnitude. So in the first step, we found RAB. Now we're going to divide by its magnitude. How do we find the magnitude of a vector? Well, just like in 2 dimensions, it's the square root of the sum of the squares of the component. So it's the square root of the I component squared plus the J component plus the K component. That's going to give us the magnitude of RAB. So we divide individually the I, J, K component of R by the magnitude of R, and now we have U hat AB, which will also be a vector. So in this step, we are dividing a vector by a scalar. The result is another vector. Now we're going to be using this in the examples that are forthcoming, but also this unit vector we are, especially in 3D, going to be using extensively to do our calculations going forward.